Thank you, Evas. Thank you to the organizers and to the Institute for their very nice work. I'm going to talk about AM-algebras. What are they? I'm going to motivate their introduction and the problem we tried to solve with this notion. So they are a structure in Banach spaces, so I think it fits in here. But basically, this is part of Banach lattice theory. So I'll give a very short, brief introduction to Banach lattices, just three definitions. It's enough to understand this notion. I'll introduce, so as I said, I introduce the notion of AM-algebras with approximate unit and use them to characterize the closed sublattice algebras of C of K. We'll see what this means precisely. And then, if I have time, some final remarks and applications. So let me start with some very basic notions about Banach lattice. The definition of a Banach lattice, Eugene already mentioned it yesterday, but it's a real Banach space with an order that is compatible with the linear structure, that is a lattice order because we have supremum and also infimum. So this follows from having supremum. And if we set the absolute value this way, then we have this compatibility condition with the norm. The examples are these classical spaces with the usual norms, and here pointwise order, here pointwise almost everywhere order. If you just forget the definition and think about these examples, you'll mostly not be very mistaken. And I'll denote by X a Banach lattice unless I say otherwise, and X plus is the positive count, so the elements above 0, let's say. Okay, so the other definitions I need is that of a sublattice, subspace that is closed under the lattice operations. We have this notion of, okay, the dual of a Banach lattice. I mean, you take the dual just like in a Banach space, but you also have a natural order defined this way for functionals, and this becomes a Banach lattice itself. We have the notion of a lattice homomorphism, so an operator between Banach lattices that preserves the lattice operations. In fact, it just has to preserve the supremum. And okay, an example of a an example of a lattice homomorphism that will be important is that of point evaluations in C of K. Remember that in C of K, the order structure is pointwise, so these are actually lattice homomorphisms. With these definitions, I introduce the notion of, I don't introduce, this is a classical notion of AM spaces. These are the Banach lattices that satisfy this particular condition of the norm. So the norm of the supremum is the supremum of the norms for positive elements. And we also have this notion of IM space with units. So if we have an element that somehow is related this way with the norm, in particular, this set must be non-empty for every x, then in this case, X is said to be an IM space with unit, and E is called a unit, an order unit, a strong order unit also. Why this notion? Why examples of this? Okay, of course, well, first of all, why this is an IM space with unit? Because when the norm is defined this way, in particular, the IM space condition is satisfied, of course. And we have that C of K is an IM space with unit, the constant one function. This is just the definition of the uniform norm, of course. And every closed sublattice of C of K will satisfy this relation that C of K satisfies because it has the same norm and same lattice structure because it's a sublattice. So these are examples of IM spaces. Are there more examples? Well, essentially, no. And this is the very classical result by Shizuo Kakutani from 1941. He published in Annals that every IM space with unit is lattice isometric to a C of K for some appropriate compact K, with the unit going to 1. And then what about AM spaces that may not have unit? Well, they are isometric to the closed sublattices of C of Ks. Moreover, in this theorem, he gave a more precise description of this closed sublattice, they are all always of this form. Okay, these are very classical notions in the theory of Banach lattices, but C of k, maybe an interpretation of Kakutani's theorem, okay, is a condition, an intrinsic condition that you give on Banach lattices that characterizes when we can embed this Banach lattice in a C of k, respecting, of course, the lattice structure. But C of k also has a natural algebraic structure, of course, the pointwise product, the typical algebraic structure that is somehow compatible with the lattice structure in several senses, but maybe the weakest is that the product of positive functions is positive. When this happens, we have a Banach lattice structure, a Banach algebra structure, and the product of positive elements is positive, we say we have a Banach lattice algebra. So now the question, this question now seemed very natural to me. Okay, when can we make this embedding of an IM space so that it is also a subalgebra of a C of k, not only as a sublattice, but also as a subalgebra? Okay, when you have a closed subalgebra of a C of k, this is already a sublattice. But here I'm always going to talk about sublattice algebras. The sublattice part is redundant, of course, but the thing is that I have a lattice. Maybe I have a product in my lattice. Let's say I have a product in my lattice. Can I embed it in a C of k in such a way that the embedding not only preserves the lattice structure, but also the algebra structure? Or if we take this interpretation of Kakutani's theorem, can I characterize the sublattices that are also subalgebras? Of course, the subalgebras of C of k are the C-star algebras, but my viewpoint is the commutative C-star algebras. But my viewpoint is that I start with a sublattice, and I want to know when it embeds also as a subalgebra. And the idea is to give a result analogous to this one here. Okay, so let me go straight to the point. So we need to find an appropriate compatibility condition between the IM space structure and the algebraic structure. And there was already a result in the literature that pointed in the correct direction. So there is this result from the 1980s that when you have an IM space with unit, if you remember the definition, well, you can say, okay, if I have a product and this product makes this unit an algebraic identity, just like what happens in C of k, then this space, what can this space be? Well, it can only be C of k. This is the result by Martignon. So now you're asking for this compatibility condition that the order unit is an algebraic identity, to put it in simple terms. And so it seems natural to introduce this definition. We'll see later why. But we say that an IM algebra with unit is you have an IM space with unit and a product, and the unit, the order unit, is an identity for this product. But can we extend this to general IM spaces? How can we do this? Because now we don't have an order unit. Then you can simply say, let this be the algebraic identity. Now, how can you establish this relation between the IM space structure and the algebraic structure? Well, there is this elementary characterization of order units that says that an order unit is where the positive functionals attain their norm. Okay, of course, in general, this will not exist, but if such a thing exists, this is the order unit. And this led us to the following notion. So we'll say that a positive net is, an approximate of the order unit if every positive functional eventually attains its norm at this net. So this, I hope that you see why this is an approximate order unit, taking this characterization. So it seems natural. And again, if you have an IM space with approximate unit, it is actually an IM space, because I put the IM space word in the definition, so this should work. And it does. Actually, this is equivalent to being an IM space. It's just another way of putting IM spaces, maybe more precise. It's not like I only have this condition that the supremum of the norm is the norm of supremums, but in particular, my approximate order unit is this net. And now the definition writes itself, because doing the same as for AM-algebras with unit, I just say, well, when this is an approximate identity, this notion from Banach algebras, I just ask for the two to coincide. So I say that a Banach lattice algebra, remember, a lattice structure and an algebraic structure, is an IM algebra with approximate unit a certain net, if this net is both an approximate ordered unit and an approximate algebraic identity. And hopefully, with this definition, I reach the desired characterization of the AM spaces that can be embedded as subalgebras of a C of K. And in fact, this is it. So I just remember you of how Kakutani's theorem read, because I'll now enunciate something analogous, which is this. So, okay, this is the result by Martignon, just in the new terms. An IM algebra with unit is a C of K isometrically, but an IM algebra with approximate unit can be embedded as a sublattice algebra of a C of K, just like IM spaces are embedded as sublattices of C of K. And more precisely, we can go a bit further, maybe change the K appropriately. We can embed it as an ideal. So actually, as a consequence, we have characterized the IM spaces that can be embedded as ideals in C of K, not only as sublattices, but as ideals. And yeah, this is the main theorem of our work. Oh, okay, I didn't mention, this is together with Pedro Tradacete, my PhD advisor. It was on the first slide, okay. And yeah, that was the main theorem. Now, maybe some consequences, maybe applications, I don't know what I have time to do. Okay, just to mention for the experts that may be bored at this point because it's very basic, but how do you do this? Okay, you pass to the bidual, you use what are called arranged products. These are just the main ingredients. You use arranged products, you use arranged regularity. It turns out that since L1 does not embed, lattice embed in this space, it's arranged regular, and then you use the result by Laura Martignon. This is the steps of the proof, I'll just say that. And okay, I recalled you the main definition of approximate ordered unit. And what do we have after this theorem? We can extract several consequences of this definition. So, okay, first of all, approximate ordered units, it's not a completely trivial notion. I mean, they may not be bounded, or even we have an example of an approximate ordered unit that has no bounded tails. Even if a Banach lattice algebra has approximate ordered units and it has an identity, not even approximate identity, but an identity, it may not embed as an IM algebra. So it may not be an IM algebra with approximate unit. That is to say, it may not embed in a C of K. So you really need this compatibility condition. And this was not obvious from the definition, but now it's trivial. If A is an IM algebra with approximate unit, then actually the positive unit ball is an approximate order unit, an approximate identity. This we know a posteriori because now I am inside of a C of K. But just from this definition, why should the unit ball become an approximate identity? Let's say that this is an approximate identity. Why should this be an approximate identity also? It is not clear to me, at least. And okay, this is just some reformulation of what just already said. And so as I mentioned at the beginning, of course, the closed subalgebras of C of K are a sublattice and are commutative C-star algebras. So this actually somehow tells us the relation between C-star algebras and Banach lattice algebras. And to formulate this relation, I did it over the complex field because, of course, it's a natural complex field for C-star algebras, whereas the natural field of scalars for Banach lattice algebras is the real. But you can complexify the Banach lattice algebra notion and reformulate all of this over the complex field. So. Okay, so how do we complexify a Banach lattice? Well, we take this, its complexification as a Banach space, let's say, and define this supremum. We call this the modulus, and this exists. We define this new norm, let's say. Here, the norm without anything else is the old norm because this modulus of Z now lives in X. And this becomes a complex Banach lattice. The relation to this complex Banach lattice to the original, this is a complex Banach space. And the relation between this complex Banach space and the original Banach lattice is the same as the relation between C and the real numbers, the complex and the real numbers. So you can think about that. It's pretty good intuition. And any Banach space of this form is called a complex Banach lattice. Here is trivial, also a simple example, really. It's just what I mentioned. And it turns out that you can also complexify the notion of Banach lattice algebra because you can define a product in the obvious way. And this now becomes a complex Banach algebra because the modulus is submultiplicative. This is not obvious, but it works. And this is what it's called a complex Banach lattice algebra. Now a natural question that arises that basically it's solved by the previous theorem, but it's, okay, I have a complex Banach lattice algebra. I have a positive cone there, namely the positive cone I had from my original Banach lattice. So can I endow this Banach algebra with a C-star algebra structure such that the positive elements in the C-star algebra sense coincide with my original positive cone? I mean, the question is when I can do that. Not always I can do that, but when can I? And the answer, of course, now it's obvious because you can do that precisely when you can embed in a C of K. Because, well, this is classical from C-star algebras that if your positive cone has a lattice structure, then you are commutative, and the converse is just what I mentioned before. And okay, I think I have another application. I'll skip, and I'll go to some further work I'm doing right now. Because a natural question is now, well, okay, you characterize, let's say, the products that make an AM space embeddable as a subalgebra in a C of K. But is there always such a product? How many products are there that do this? And I think I have answers to this. So you don't always have such a product, but when you do have this product, it is unique. There are several nice characterizations of when do you have such a product. For instance, when you embed as a closed ideal in a C of K, and also some more technical conditions regarding weak star continuity of the norm in certain specific subsets of the dual. And once you have this product, what does this product look like? If you have it, it is unique. And how does it look like? It turns out that there are also very nice characterizations of it. For instance, this one, which may seem a little weird. I mean, the unique product for which the norm 1 lattice homomorphisms are also algebra homomorphisms. This is very nice, actually, because the norm 1 lattice homomorphisms in a C of K are the deltas. So in a C of K, this is precisely the definition of a point-voice product. It turns out that, well, it won't always work in an IM space, but when there is a product like this one, this defines it completely. So there is no other product satisfying this. And also another characterization is, well, lattice embed your lattice in a C of K. If you can do that in such a way that it is a subalgebra, restrict the product to your X, and this is the product I'm talking about. And this is perfectly well defined. So you can do it in any way, and this works. And of course, when the AM space has unit, everything reduces to the point-wise product. So this is somehow a generalization of the point-wise product to more general AM spaces. And okay, so I think we can generalize many results from the C of K setting. So the case where you have when you have an ordered unit to only when you have approximate ordered units. And many familiar examples of AM spaces admit such a product. So it is natural to consider this product in the theory, well-studied theory of AM spaces. And as I said, several results that relate the lattice and algebraic structures of C of K can be extended to these general AM spaces that admit this canonical product. And I finish here. These are the references for the results I mentioned, and thank you very much for your time.